I begin with a simple, startling thought. What if the world you pass through each day is full of invisible dramas, tiny battles, silent performances that shape everything you see? In the next few minutes, I will take you on a quiet journey, the scent that reaches your nose, the blackness of space above, revealing the hidden rules that govern ordinary miracles. You will hear facts that sound almost like magic. Why perfume spreads even in a still room, why a flame can turn green, why space itself appears dark despite the sun's brilliance. And each will be explained by something profoundly simple and surprisingly elegant. By the end, you will not only know these facts, but understand the gentle physical laws that make our everyday world both predictable and endlessly wondrous. Expect a few surprises. Number 7 is truly wild. And, a clearer view of the ordinary miracles that surround us. Have you ever wondered why perfume fills a room even if there's no breeze? The answer lies in the restless motion of molecules. At a microscopic scale, perfume molecules move ceaselessly, a jittering dance we call Brownian motion. When a concentrated perfume plume meets clean air, those restless molecules spread from high concentration to low, a process called diffusion, until the scent is evenly dispersed. The secret is molecular energy. Heat speeds up water molecules. Heat also speeds up sugar molecules. Faster motion means more frequent collisions, and more violent collisions. Each impact can free sucrose units from the crystal. Crystalline chains break apart. Water molecules rush in and surround single sugar molecules. Water's polar nature stabilizes them and prevents rejoining. The result, granules turn into an invisible, even solution. Stirring amplifies this by bringing fresh, energetic water to the sugar. But temperature is the main accelerator. The spoon in a steaming cup is an orchestra of microscopic collisions. Those countless collisions transform a visible grain into invisible sweetness. When metal strikes metal, why do bright sparks leap out as if miniature stars were born for an instant? The drama begins with the violent contact. Flakes and fragments of metal are torn free by the impact. These tiny particles are compressed and heated to very high temperatures in the split second of collision. Once exposed to the oxygen-rich air, the incandescent metal fragments oxidize rapidly, burning as they fall, and so we see bright, fleeting sparks. Magnets can seem selective, attaching fiercely to some materials while ignoring others. This selectivity is rooted in the quantum world of electron spins. In certain metals, notably iron, nickel, cobalt, groups of electron spins can align over large regions to create domains with a unified magnetic orientation. When an external magnet approaches, these domains can rotate or grow so that their fields align with the magnet, producing attraction. In contrast, metals such as aluminum, copper have electron arrangements that do not favor such long-range alignment. Their tiny magnetic effects cancel out, and the magnet senses nothing. Temperature and atomic structure matter too. Heat can disorder spins, weakening magnetism. Crystalline arrangements determine whether spins can cooperate. Thus, the magnet's apparent preference is simply a reflection of how electrons choose to behave inside different atomic lattices. On a cold morning, you may see your breath as a ghostly cloud. The breath we exhale is warm and saturated with water vapor. When it meets the colder ambient air, its capacity to hold moisture drops sharply. The excess water vapor condenses into myriad tiny droplets, minute liquid spheres that scatter light and appear as a mist. These droplets are similar to clouds and fog, formed by the same condensation physics, but on a much smaller scale and for a shorter time. Humidity and temperature difference determine how dense and long-lived this breath cloud appears. On frigid, dry days, the contrast is greatest and the mist becomes conspicuously white, a visible fingerprint of the water we carry out of our bodies into the world. We have all seen oil floating serenely on water, refusing to mix. a stubborn separation that stems from chemistry. Water molecules are polar. They carry an uneven charge distribution and create a network of hydrogen bonds with each other. Oil molecules are nonpolar and lack the electrical character to join that network. When oil meets water, it cannot form the hydrogen-bonded connections that keep water molecules together, so the two liquids minimize contact, forming distinct layers. Surface tension governs the shape of those layers, and the lower density of many oils makes them float atop the denser water. Emulsifiers, like soap, can bridge the gap, and a tail that likes oil, allowing mixtures to form. But without such intermediaries, oil and water remain content to keep their separate identities. Flame colors can dazzle and deceive. Green of copper, brilliant yellow of sodium, and the cause is a gentle quantum choreography. When an element is heated, its electrons absorb energy and leap to higher states. As they return to lower levels, they release photons of very specific wavelengths. These emitted wavelengths correspond to characteristic colors. Sodium yields a vivid yellow, copper often produces green or blue-green. Other elements produce their own spectral signatures. In a flame, tiny particles or salts evaporate and provide a rich palette, so adding a metal compound to a fire can turn it into a living aurora. This is the same principle behind fireworks and flame tests in chemistry. Each color a fingerprint, each spark a small, deliberate revelation of the element within. Look up from a clear night, you see an ocean of black punctuated by stars. Why is the vastness between them so dark? The answer is tied to the absence of an atmosphere to scatter sunlight. On Earth, molecules in the air scatter shorter wavelengths of sunlight, painting our sky blue and diffusing light in every direction. In the vacuum of space, there are virtually no particles to redirect sunlight toward your eyes, so the space between luminous bodies remains dark. Stars themselves are bright points because they emit their own light directly into our line of sight. But between them, there is nothing to illuminate. Even though the sun is immensely bright, without scattering or a medium to carry that light across the void, the regions away from direct beams remain profoundly black, a reminder that brightness requires not just a source, but a path. When you drive, the tires under you grow warm, a fact born of energy-shifting forms. As rubber meets road, microscopic deformations and slippages occur across the contact surface. Friction converts kinetic energy from motion into heat within the tire material. The faster you drive or the harder you brake, the more intense these interactions become, producing greater heat. Heat also builds from flexing within the tire as it rotates, a cyclic bending that dissipates energy as thermal motion. This rise in temperature affects tire pressure and wear, and is why drivers watch for overheating under heavy loads or sustained high speeds. What begins as motion is ultimately exchanged for heat in a quiet, inexorable transformation. Rubbing alcohol cools your skin because evaporation demands energy. Energy that must be borrowed from the surroundings. Alcohols like isopropyl have relatively low boiling points and vapor pressures, so their molecules escape into the air readily at room temperature. As those molecules leave the liquid, they take latent heat with them. When alcohol is on your skin, the heat drawn away is taken from your skin's surface, producing a perceptible cooling sensation. The process is essentially the same as sweat cooling you, but faster due to the alcohol's volatile nature. Care is needed, for rapid evaporation can also lead to chill or dryness. But the underlying physics is beautifully simple. Phase change consumes energy, and the environment feels the loss as cold. We have walked together from the random wanderings of perfume molecules to the deep, uncompromising black of space, and in doing so, we have lifted the veil on the simple science that underpins everyday wonder. Each fact we explored, from dissolving sugar to colored flames, is a doorway to a deeper appreciation of the laws that quietly choreograph our lives. If one revelation surprised you, tell me which. Did you expect breath to be miniature clouds or flame to be a coded announcement of elements within? Please like, subscribe, leave a comment with the fact that astonished you most. Your response helps shape the next journey we take.